MIT, MSR, Harvard Reverse Algorithmic Game Theory workshop on applied econometrics, organized by me, Bobby Kleinberg, Glenn Weil, and Ricardo Perez-Trivia. All of us are at MSR. This is the, I think, fifth workshop in a series entitled, somewhat cryptically, Reverse Algorithmic Game Theory, where I gather the objective of the workshop is to invite economists, some very good ones, as you can see from today's list of speakers, to come and tell us about problems they're interested in that may have an interesting computational dimension. And the word reverse in the title of the workshop I interpret as a possibly humorous, possibly caustic commentary on how this constitutes a reversal of the standard practice of algorithmic game theory, which is computer scientists getting up and trying to convince economists to be interested in our problems. If you don't like that interpretation, don't blame me for the name reverse AGT, but do feel free to blame me for that spin on it. Today, all of our talks are going to be about applied econometrics, and I think that our vision is to have an interesting, multifaceted discussion about the different ways that economists look at drawing conclusions from observational data, and how these relate to the way that computer scientists, especially people in machine learning, have been grappling with some of the same questions about drawing conclusions from data. With that, I will turn the floor over to our first speaker, Emily Oster of Brown University, who's going to be telling us about causality, approaches, and pitfalls.
Okay, so
each segment, I should say, is going to be 30 minutes of talk and 15 minutes of questions.
Okay, so let me first apologize. Obviously, I've lost my voice, and as a result, if you can't hear me, I'll try to talk louder. And I'm also probably going to leave shortly after my talk to go back to bed. But hopefully we will have some good discussion in the talk, and then you can always email me later if you want to talk more. Okay, so what I'm going to do is basically give you a very short version of an applied econometrics class, which will overlap a little bit with kind of some of the stuff I think about, and I'll try to highlight where I think there's sort of questions that I'm interested in. But this is going to be, I think, more so than Max or Sendel, kind of like a little bit of sort of an overview, and hopefully then they can tell you, Max like an actual econometrician, whereas I am like a person who works on health. So there you go. Okay, so here's the basic Rubin causal framework setup. There's an outcome Y, there's a treatment T, there's a covariate vector, like a vector of controls X. So think about the classic example in the treatment effect estimation literature is job training and wages. We have people's wages, we have whether they had job training, we want to estimate the causal impact of job training on wages. In my space, I'm more interested in things that are about health, so a low-fat diet and heart disease. The outcome is you have heart disease, the treatment is you have a low-fat diet, and you can think of the X's as being characteristics of people. Their age, their gender, their education, whatever. And then we're going to have, this is a potential outcomes framework, so there's a person I, they have a potential outcome, like a potential wage, if they get treatment 1. So if they get job training, there's some potential wage. If they don't get job training, there's some potential wage. Those are YI1 and YI0. What's the impact of treatment on Y? Well, that's the thing we want to figure out. If you gave this person treatment, what would happen to their wages? And that's just the expectation of the difference between those two objects, their outcome with the treatment minus their outcome without the treatment. Okay, the problem is, the sort of classic problem here, is that you do not see both of these outcomes for the same person, right? So everybody either has treatment, they don't have treatment, it's a binary thing. And so you observe either YI1 or YI0, and you cannot see the thing that you want. Well, there are different things you can see, but a simple thing that you can see is this. So the average among the people with the treatment, average wages among people with job training, and average wages among people without. And what's the problem? Well, obviously the people who get the treatment are sort of systematically different than the people who don't. And it doesn't take a lot of economics to think about, what kind of people go engage in job training. It was like the kind of people who like care about things and want to do better. And of course, those people have higher wages, but how do we know it's a job training versus something else? If you think about like the diet example, it definitely is the case that you would observe that like people with a low-fat diet who eat a low-fat diet have less heart disease than people who eat a high-fat diet. But there's like 50 million things that are driving that effect. Some of them could be the low-fat diet, but that's like hard to know in the data. Okay, so that's the problem. And then the question is, what can we do that would actually generate a causal impact? So I'm gonna stick with the diet example because I like it. And let's just in fact just think about mortality. So here, like the outcome here is just did you die? And this is like a little. I mean, of course you're gonna die, right? But everybody dies. But this is like did you die by some date or some hazard or whatever? Treatment is did you eat a low-fat diet, and X is like other stuff, things about you. And so a sort of gold standard, I'm going to talk about like what is the gold standard, how would you actually figure this out, like what would be our sort of causal gold standard. I'm going to talk about sort of things that I think of as options that kind of you could do with like the NHANES. Okay, the NHANES is the National Health and Nutrition Examination Survey. It is like a nationally representative observational data set that you can download off the internet, and you could be up and running on the NHANES about 20 minutes. And so there's like some things that I'm going to imagine like that's our observational setting. Like how much progress could we make there? And then I'm going to talk about sort of options that I refer to as things with special data requirements in the sense that there have to be something in the data that you would be using. I don't think people often think about it quite like this, but as I've taught this to economists, to like grad students, I actually think this is kind of a nice way to sort of separate out some of these identification strategies. Okay, so the gold standard is in RCT. I'm not really going to talk much about that today, but like you sort of think about what is this, how would you do this? Well, you like recruit a bunch of people. You would randomly tell half of them to eat a low-fat diet. You'd follow them over time and see if they die, and then you'd see whether they die sooner with the treatment and with in the control. Well, why does this work? Well, obviously, you're turning off all the other differences across people. So then when you just compare the outcomes for treated to the outcomes for control, they're balanced on everything else. There are the obvious downsides for this, like why are we even having this discussion about observational data? This is expensive. It takes a really long time. Actually, there are RCTs of low-fat diets. There was like a period when all of a sudden the government decided like the low-fat diet is really good for you and like you shouldn't have any more cholesterol and so on. And that was when we were kids and they used to get to eat eggs, and then it was like no more eggs and you should have cereal. And then they actually ran some RCTs. That was motivated by results in observational data. And then they ran some RCTs, and it turned out like that was completely made up, and actually low-fat diet, you're basically dead for that. But that was like many years, it was like our whole childhood, no eggs. And then eventually it's like, actually eggs are really great for you. So this is the kind of thing, there are downsides. Okay, so we're going to talk about the sort of example of this, and it's like a typical kind of what you'd have in observational data. So this is a data set. It's actually quite good for observational data. So it's got, it's like big, nationally representative. It has dietary information. You think like actually you know what people eat. It has good demographics, so things like education, income. It has other things about their health, and you can link it to mortality. So it's a data set in which you could, in principle, estimate things, and many people use these data to do various things. So let's think about just what could you do with this. And I'm really going to sort of talk about two kinds of options here. So one is what we call selection on observables. And the other is the idea of selection on unobservables. And I will say the second of these is something that I work on a little bit. Okay, so here's the selection on observables math. So consider basically the expectation of outcomes for people with treatment of one conditional on their covariates, and the same thing for 0. And basically this is just like, Max is probably like, I probably got the notation wrong, but basically what you want to think about is a regression of y of outcome on the treatment controlling for this stuff. controlling for the stuff you see. So this is like I'm running like an OLS regression where the left-hand side is like did you die? The right-hand side is did you have a low-fat diet? And then I have like a control for your education, control for your income, a control for your race, your gender, and those are my axes. In principle, this could uncover a causal effect. The assumptions under which that's true are that the treatment is randomly assigned conditional on the stuff that you see. Okay, so if in fact like the only other things that matter for whether you die are the things that you observe, you the econometrician, the computer scientist, observe in the data, then you can get a causal impact out of this. Okay, so like practically you want to think like, is there anything else that's different between treatment and control, between the low-fat guys and the high-fat guys, other than the stuff that I see in the data? I mean, so this is sort of nice because you can definitely do it. And if you look in like public health journals at like papers, this is basically the procedure that they're mostly using. Is they'll kind of stick in a bunch of controls and they'll say, well, I'm like adjusting for covariates. You can read that a lot, like I'm adjusted for covariates and the effect was still significant at the 7% level, so it's definitely true. And it's a common people like that. But it's tricky because of course you frequently do not think that the treatment is randomly assigned conditional on observables. So in this particular example where the treatment's diet, a sort of common set of covariates would be something like, did the person go to high school, did they graduate high school or they graduate college, like 3 or 4 categories of education, 3 or 4 categories of income, race, age, gender. And then you think like, are there any other things that differ among people other than like whether they went to college and the 3 categories of income? Well, like yes. And is it possible that those things also correlate with their diet? Yes. Okay, and so it's like not enough. And in fact, sort of this is kind of all you can get to is like it's not quite right. Now, you can actually go a little bit further. You can probably say what the sign of the bias is, because this is sort of a standard we call standard omitted variable bias problem. And so you basically, is your effect too big or too small? That's something you can infer by thinking about the relationship between the treatment and the stuff you don't see, and the treatment and the outcome. Yeah.
Something that puzzles me on the slide, which is the equation in your first.
I already told you that, yes, it's probably wrong, but yeah, go ahead.
No. In your first bullet is a function of the values of the x2. The expression that you've written down is not a number. It's something that would say, well, the effect is positive when your income is in this range and your race is that and your age is that, and it may be negative when your control variables take some other value. So as written, even if t is random conditional on x, the experiment might produce an ambiguous answer that says the effect size depends.
Yes, so there's sort of like 2 responses to that. One is partly I just probably should have written it differently, but there actually is a sort of something that's true in there, which actually you can get out from this heterogeneity across people in the treatment effect. So you could actually sort of go, one of the things that's very good about this kind of setting is there's no reason you could not estimate a heterogeneous treatment effect and estimate a different treatment effect for each group. Now, of course, there's still within each of these groups, you're going to have a difference. You're going to have characteristics that differ, probably that cause there to be bias. So it's like you could say one approach is to basically take each of these sort of like groups, basically people with a college education, with a high income, who are women, who are in a particular age cohort, and estimate a treatment effect for them. And that would be like an extreme version of adjusting for observables in the sense that you're adjusting not sort of linearly, but like for each interaction, you could estimate a treatment effect there. You're still only as good as sort of the idea that the treatment's randomly assigned within that. But yeah.
Maybe related to that, Emily, is there a, you might think that like I'm going to do this by linear regression probably, but I could be doing something kind of more MLE, and obviously I can't fix the bias from omitted variables. But I wonder if you have any sense of whether like the public health thing estimates would become better just if we started to do something a little bit more sophisticated about blocking things and allowing for nonlinearities.
Yeah, so I think so I'm actually like part of where I sort of come down on this stuff is I actually think we aren't using this technique as completely as we could. Right, and so in some sense, when people do things with selection on observables, one pitfall is that they just like pick four things, and they're like, oh, these are the only 4 things. But actually, your data set may contain many more things than that, and this is, and those things may interact with each other. And so part of where this is actually a place where I think the machine learning stuff sort of comes in a potentially quite useful way. Because if you say basically, now I'm going to take everything I observe in the n-hands. I'm going to have your mom's education, your dad's education, all of your things about your siblings, other stuff that happened to you. Like, I don't know, there's a ton of stuff in this data. And I want to interact all that stuff with each other. Well, you can't estimate that, it's a finite sample size. But you could imagine running some kind of lasso on the sort of the prediction of the treatment with those things, seeing how well you could do on predicting the treatment, and then doing basically a much better job on selection in the selection on observables. And that would likely reduce your bias. It's unclear sort of, you'd still potentially have this problem, but it's like, yeah. So I think the short answer is we could do much better with even like a better form of selection on observables. Yeah.
You had said something that confused me like 5 minutes ago, which was you can tell the sign of the effects due to the unobservables?
Yes.
How do you like?
Okay, so can I like put this up? Can I write on that board? Can I write? Okay. Yeah. So this is actually like kind of neat. So. Okay, so here's your treatment effect equation, and this is like what we call your true model. So basically, y is a function of the treatment, and let's just say there's just one covariate, x. And now think about what you can really estimate, which is basically you can only estimate it with the treatment. You can't see, like this is sort of the omitted. It's like there's something I can't see, which is x. I can only see the treatment. So what's the so what's the difference between beta hat and beta? Well, think about the relationship between x. I always write this in the wrong. I want to make sure I write it in the right order. Yeah, between x and t. So think about a linear regression of x on t. What have I not used? Delta. And so now that we've posited there's some relationship between x and between x and t. Now think about putting this in here. I promise I'm going somewhere. So now we have y equals alpha plus beta t plus gamma mu plus delta t. So now if I estimate only, if I think about this beta, it's basically the beta I estimate, beta hat, is the true beta plus the product of these two things, plus gamma times delta, where gamma is the impact of x on y and delta is the impact of t on x. So it's basically like the product of those two things. And so that in that sense, you can sign it. Basically, if you knew the direction of the relationship between y and x and the direction of the relationship between x and t, which you almost always do, at least for you frequently do, then you can actually say whether your estimate is an overestimate or an underestimate. Does that make sense? Yeah, okay. Okay, so that's selection on observables. Now, I think we can sort of go a step further, and this is yes, please. No.
Question. In practice,
yeah.
I assume that omitting unobserved variables usually leads to overestimating effect sizes rather than underestimating them. Would you say that's true?
It's interesting. Basically, yes. I mean, like there's no kind of reason that would have to be, but I think it is often. Let me put it this way. In practice, yes, because like most of the settings where most of what happens is like people like to publish significant results, and so like the things that you see published, then like they're like biased away from 0. But there's no reason that your omitted variables couldn't push you the other direction. In these like diet kind of examples, it is always going to anything where it's SES, it's always going to be like away from 0. Okay, so now let's think about the sort of extension of this. Like you've put in some observables, but of course, there are basically controls that you don't see. There's other things that you don't see that are also unobserved. So in public health, they call this residual confounding, okay? And in economics, we just call it omitted variable bias. It's just the same idea that basically there's like stuff that you see, you can control for that. There's stuff you don't see. And basically, without saying anything else, you cannot address these problems. If you don't see the things, then you can't do anything to adjust for them. And so one of the things that I have worked on is the question of like, what additional assumptions could you add that would let you say something about those, and not so much say something about a point estimate, but say something about bounding, right? And so there's sort of an approach in this space, which I would kind of describe as like asking, like sort of assume that your observables are kind of like your unobservables. There's different ways to formalize that, but it's like saying assume, what I see in the NHANES is 3 groups of education, 3 groups of income, race and gender. But what I'm worried about is that although I see like whether you went to college, I didn't see where you went to college. And there are like very big differences across, quality of college between, community college or between Brown and Harvard, right? And there's very big differences there, and there's big differences in where whether you went to graduate school, how well you did in college, whether you know anything about data, who knows? There's like a lot of differences across people that are not captured. But there's a sense in which those effects are kind of like the things we see. We sort of see, we think like the difference what happens when you control for like whether someone went to college, that's kind of selected, related to the treatment in the same way that these sort of more detailed things would be related. Okay, so it's like somehow you're learning, you can potentially learn something about the unobservables by knowing something about the observables. So if you are willing to make an assumption about that, basically an assumption about the relationship between the unobserved variables and your treatment and how that is related to the relationship between your observed variables and treatment, you can then sort of bound the bias. So this is kind of more of a bounding idea. Basically, we could try to make some progress on thinking about how much bias is left. Is it likely my true effect is 0? So I sort of I think the simplest example way to explain this is there's a lot of literature on the relationship between breastfeeding your kid and their IQ. Okay, and the relationship between breastfeeding and IQ is like people think it's positive. Okay. But it has this problem that like rich fancy ladies like to breastfeed their kids, and the other people don't do as much of it. Okay? And so when you see papers like this, I would say a very strong pattern would be something like this. No controls in the regression, 4.5 IQ points for breastfeeding your kid. Put in controls for whether the mother went to college and how old she was when she had the baby, effect 1.7 percentage points significant at the 10% level. And people are like, well, it's very large. Still very significant. And you sort of, what is our intuition about why that can't really be right? It's like, presumably you have the intuition, like if you could only see a few other things about people, it would be going down even more. And so this is kind of a way, there's some ways to sort of formalize that relationship. Okay, again, see Bobby is looking at the clock. What, I get like 5 extra minutes after, okay. All right, so things that are like sort of improving selection on observables, thinking about selection on unobservables.
You keep doing such a good job answering our questions in the middle of your talk.
Right, then I get, okay, excellent. So I think the advantage of these sort of kind of ideas is that actually these techniques can work even if your data, basically with data that you can get online. And so I think economists have not, as part of our kind of credibility revolution, we have pushed a lot on the techniques that I'll say something about in a minute, but much less on this sort of what could I do with just the observables? And I think to me, this is the place where these machine learning techniques are likely to come in most strongly, because I think it may help us improve this stuff. And the truth is that because these techniques do not require anything very special, they are a lot of what people do, and we're trying to learn things from them. And I think that's kind of that has real value. Okay. All right, so there's a lot of special data techniques. I basically think these are all the same in some sort of particular sense. So let's think about some variable z, which for some reason randomly pushes some people into treatment. Okay, just like it's just something that pushes people in treatment. We can talk about what that means. And now imagine like isolating the variation in treatment that is due to the variation in Z. But Z is like otherwise totally unrelated to the whole system. It's just like some, random thing. And now we're going to like basically use that part of the variation to estimate the impact of treatment. So this would be something like people live different distances from job training centers, but the job training, but otherwise that's unrelated to anything. And so there's a part of whether you get job training, which is just like about how far you live from the center, which is otherwise unrelated to your IQ or like your wages or how hard you work or whatever. And we're going to try to use that part of the variation to estimate the effect of job training on wages. There's a bunch of things in this space. The two I'll probably talk mostly about is regression discontinuity and IV. Here's like a fake regression discontinuity example related to our diet thing. So let's imagine that doctors adopted a new rule, which is that when people have a BMI over 25, they're told to go on a low-fat diet. If a BMI is under 25, they're not told. Most regression discontinuity analyses, particularly in my space of health, rely on the fact that doctors are like obsessed with cutoff rules, and they like to just like they really like cutoff rules. So this would be a totally plausible rule. So now we've got like two people. There's a guy whose BMI is 24.9. He was not told to go on a low-fat diet. There's a guy whose BMI is 25.1. He was told to go on a low-fat diet. There is no other difference between these people, right? I mean, this is just like, did one of them eat breakfast before he came? He like stop at McDonald's for the all-day breakfast. The other one like didn't know about the all-day breakfast yet. And so those are like they're the same. These guys are the same. And so, but of course, there's like this random determination of what kind of diet advice they got. Now, this example isn't so good because no one actually listens to this, but if people listen to their diet advice, you could use this. You could like use this idea to get a causal impact, and it's the way people do it is very simple. Regression discontinuity is always in a picture. So here's your picture. Here's your like weight change, okay? And here's your BMI, and it goes from like 23 to 27. Here's 25. And what you want to see in your picture is that's a regression discontinuity picture, okay? It's like flat, 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 and then there's like a jump up that occurs right at the change in the advice. Okay, and then you're going to basically say from this, look, these two people on either side of this, other than this issue about the low-fat diet advice, this is a weight loss number. Anyway, other than this issue about low-fat diet advice, these guys are otherwise the same, and so you're going to attribute that thing to the change. Okay, so that's an RD picture, and anytime you see an RD paper, it's going to have a picture that looks like that. Yes.
So you're basically saying that if people do follow this advice, and if you run regression on weight loss and BMI, and you will be able to observe the difference, and that difference contributes to how much this affect here.
Yes, exactly. That's it. And so if you like basically in these kind of papers, that difference there, that jump, that's the effect. And it's because you're saying basically as you narrow in around this cutoff rule, the people are kind of otherwise very similar, except for this difference in advice. So this isn't a very good example because of the fact that like people don't listen to diets, and there's no rule like that, but like people have used this in birth weights. So there's like a very strong cutoff about what you define as a low birth weight baby. It's like 1,500 grams. And so they've actually looked at mortality, and you can sort of see this kind of graph that babies that are a little bigger than that die more than babies who are a little smaller. Okay, so like, what's the problem with it? What's sort of the downside of this approach, which basically is kind of very nice, and I think it's particularly great that you can like see it in a picture. That's like the best. So I think that like a major issue is this effect is sort of specific to the characteristics off of which you identify. This gets back to the heterogeneity point. I think we do stuff with sort of observables and kind of, we can estimate heterogeneity. We can think about applying all the same kind of ideas to particular subgroups. This is going to tell us the impact of weight loss of this low-fat diet around a BMI of 25. It's not that number isn't interesting. That just may not be the same number as the effect at like 27 or 40 or 45 or whatever. So you're basically like, and there's kind of no other people that you can use. You can only identify the effect for this group. So if you're willing to assume treatment effects are homogeneous, fine. Once you allow for the idea that treatment effects might be heterogeneous, then you kind of you've only learned about that little group. The also sort of other obvious thing is that you actually have to have a discontinuity. So you can't just like download the NHANES and be like, okay, let me like make an RD. There actually has to be a regression discontinuity, and so that sort of limits how frequently you could use this. IV is the other thing I wanted to say something about. So I thought about a good example for this. This one wasn't so great, but let's say there's a religion that requires being a vegetarian. On average, vegetarians eat less fat. The sort of key assumption here, which what we call the exclusion restriction, would be something like religion does not otherwise affect your mortality, so like, which is probably not true. So what you would do here, what people do is they relate this like this religion to the treatment. They basically predict like the fatness of your diet based on your religion. So now you have like a new sort of, did you have a low-fat diet, which is really just like a rescaling of, are you a Buddhist? And then you relate the outcome to this sort of predicted treatment, and effectively what you're estimating is only driven by variation in the instrument, by variation in the religion. So, and then you can interpret that causally. Really this, like I think it's sometimes lost on people, but really what I'm suggesting, what people are suggesting here is you regress, did you die on your religion? And then you interpret it as the effect of a low-fat diet. And I think that kind of highlights some of the issues with IV. So this part of why you can see this example sucks is that if you regress mortality on religion, you wouldn't first be like, oh, it's probably diet. And so you really need something that otherwise is basically random, and many instruments do not really pass the exclusion restriction when you sort of think about it like that. It is also the case that, again, you have sort of very stringent data requirements. Okay, so can I have like one more minute? Yeah. Okay. So the last thing I wanted to say something about, which kind of I think falls in this in the intersection of these two things, is the idea of the propensity score. So now let's imagine that I'm back in the setting in which I have just observables, but I know everything that influences the treatment. I just don't know like how they go together. Okay, this is like the most sort of classic. People use the propensity score in a lot of different ways. This is like I think in some ways the starting point. So imagine that I know how you get into job training. I know that the things they take into account when they like decide whether you're going to be in job training are like, how much money you made last year, and how many weeks you worked last year, and like how old you are, and I know that they do something with these things, but I don't know how they interact. Okay, so I know like all the things that go into the formula, but I don't know the formula. And I know that they like assign you a score, and then they basically randomize somehow around that score. That is a situation in which you could use what's called the propensity score and basically try to predict, like put in everything, all the interactions and everything, and try to predict what somebody's probability of treatment with that. And then you control for that predicted probability and also for the true treatment. And so then it's like conditional on your predicted chance of getting into this, whether you actually were in is like random. And that is another sort of thing where I think we kind of get into a space where the machine learning stuff is useful, because if you actually sort of know the things that enter, you don't know how they enter, that's something that you use. Okay, so causality is very hard. That's basically what I'm saying. And I see this sort of tension between the sort of strength of the causality and like the specialness or localness or believability of the effect. So some of these things like RD, like it's very nice in the sense that it gets you like a number for somebody, but it's tricky because it doesn't get you a number for that many people. And so I'm actually in some ways, like I think that econometrics should push more on some of these sort of things that you could do with just like any data that you have, and sort of improve ways that we can improve on that. It's not what you people seem to be up to, but perhaps now you can, All right, so I will stop there, and we can take, I don't know.
The first of all, +1 for the words era of big data. Kind of like,
Yeah. It's very hot right now.
Yes.
Isn't it?
I have two questions. One is more closed-ended and involves
Yeah.
the previous slide on propensity scores.
Okay.
You said regressing on all the variables that determine T would overfit.
It could, yeah. It
Instead,
depends
you're
how.
going to regress T on those variables to determine how like the probability of T depends on them. So
Yeah,
it
so I
sounds
think-
like that's just pushing the overfitting problem over to that regression.
No, it
and now
can.
you're going to overfit the probability of T.
Yeah, so I think it's yeah, it could also. So the way people would do this, they would not regress it on everything. They would regress it on some things that they pick through some stepwise regression. You could also imagine using like a lasso kind of technique for doing that. I think, and this is stretching a little bit, that like the properties of the problems that you get with the overfitting and the treatment are like better than the, I don't know. Yeah.
Okay.
Sorry.
Other question. Early in the talk when you presented the gold standard of an RCT contrasted against using N-Haynes, it reminded me in some very fuzzy, hard to grasp way of the relationship between labeled and unlabeled data in machine learning. Labeled data is this gold standard, but it's really expensive to get it, and we can't always get it. Unlabeled data is this inexhaustible resource that sometimes, in combination with a small amount of labeled data, can really help. And I'm wondering if there's been work in econometrics on applying those kinds of hybrid techniques where you have a small sample size RCT together with a giant observational data pool, and using them in combination, you get more significant results.
Yeah, so I have actually, I will say, I think there probably is some of this. I have actually been thinking about some of this kind of thing in this selection on observables idea, basically trying to use cases in which we have both randomized and observational results for the same thing to sort of calibrate like how much in a particular setting, like how much sort of unobservable bias do we think there is, and then we could use those things for things in the same setting to try to like basically extend the RCT past the outcomes or past the groups that you had. But I don't know how much, I think the interesting stuff in econometrics is not so much about RCTs. It's more like the sort of hot stuff in econometrics now is about like weak instruments. And what's the other, Max, what's the other thing people like?
That's who you ask.
Okay, fair enough.
So
Yes.
you talked a bunch about dealing with unobservables, and I felt like a lot of the ways that you presented to deal with them involved knowing what they were, even
Yes.
if you couldn't observe them. And
Yes.
there's there's the things you don't know, and the things you don't know, you don't
Uh-huh.
know. And so is the latter
Yes.
category.
Terrible. No, you can't do anything about that. Yeah, I mean, I think that's sort of the point. Like basically, like all of these techniques for dealing with unobservables are about the things which you know you're missing. If there's stuff that you like don't know you're missing, or even that you sort of know you're missing, but you basically don't see any proxy, like you just don't see anything like that, there's nothing you can do. And then basically you're like, your bias on your observables is more or less unbounded, I think.
Can you even know that there's things you don't know?
No.
I guess you could use.
I mean, the thing is, once you know that there's something you don't know, then you could try to like get some information on it. I guess really the worst things are things that you just have no idea are a problem.
Yeah, but you can tell you're missing something without being able to tell what it is because you're like not matching the RTCs very well.
That's right.
And then
Yeah.
you could,
Yep.
I guess, go look for it.
I think I mentioned this in responding to Bobby's question, is that have this method been calibrated? So in the sense of like that, suppose I have a scenario that I can do a randomized control experiment, but instead I'm just using the techniques here. Is there a way to know that how much I'm off?
I mean, there is a literature on sort of how these techniques perform relative to. There's like sort of an old literature and some newer literature. Like there's sort of in the particular job training space. There's a very famous paper by a guy named Bob Lalonde in like the 80s about kind of how well different techniques match randomized data. And so, but I mean, there isn't so much. I wouldn't say that's a way that people defend use of these techniques, but there is work on sort of how they perform.
Like, can the result be easily summarized? Are they performing relatively?
Yeah, some of them perform better than others. So no, I guess no. Not really.
I have another question about your instrumental variables example.
Yes.
I'm not sure I was getting how the instrumental variable was used there. In a hypothetical data set where I had people's mortality and religion and diet, I wouldn't have to use religion as a proxy for diet because I get to see whether they have a low-fat diet.
No, you instrument for the low. So the low-fat, the idea there is that low-fat, that what determines your low-fat diet? There's religion, which we're going to say here is randomly assigned. And then there's like, how educated are you? How like otherwise health conscious are you? Whatever. And those things are not randomly assigned. So we're going to regress your low-fat diet on religion and get a predicted value. That's going to be driven exclusively by variation in your religion, which is random. So it's going to be like this kind of predicted part of this like predicted low-fat diet, but predicted based only on random stuff. Now I'm going to regress your mortality on that predicted low-fat diet. And that's going to tell me it's really just going to rescale the relationship between mortality and religion under the assumption that the only reason religion matters is through the diet. That's it. Yeah.
Got it. Okay, so in order for the example to really shine, it has to be something like belonging to this religion increases your probability of having a low-fat diet, but there still is some randomness among the among people in that religion. There has to still be some
that's right. So you can't have it can't be the case. I mean, if religion is the only thing that matters for a low-fat diet, and it is randomly assigned, then your first stage, or what we call the first stage there, will have an R squared of 1. That will be it.
Yeah.
And then basically what you're saying is actually, although you were concerned that low-fat diet was driven by other things, it turned out it wasn't. It was only driven by religion, so you actually would have been fine. Just running the naive regression, and then your OLS and your IV will be the same. Practice, I never really.
Can I just add to that? Like, if you're doing that, then so isn't it you can just interpret the effect as the impact of religion on what you're trying to do? So why it makes sense to say that like we're getting something about low-fat diet rather than other things?
Okay,
because
so
you get the same result for whatever factor.
It's a fair point. Typically in a setting like this, actually what you're interested in is the effect of the low-fat diet variable, not the effect of religion. So this is sort of a bad example in the sense that religion is something of interest. But let's say that instead of religion, your instrument was like distance to Krispy Kreme. Okay, and it turned out like people like randomly, Krispy Kreme is like donuts, that like people were like locations were randomly assigned, like people's houses, how far they are from a Krispy Kreme donut shop. And that's random, and of course, like since people like Krispy Kreme, if you live near a donut shop, you eat a lot more Krispy Kreme, so that influences your diet. Then you could imagine, okay, I'm going to run mortality on distance to Krispy Kreme, and I'm going to get some causal effect. But nobody cares about the causal effect of Krispy Kreme on mortality. What we care about is a low-fat diet, because we don't want to just apply like to the Krispy Kreme people. We want to have a broader conclusion, which is like in general, if people ate a low-fat diet, would they die less? And we're just using the Krispy Kreme as like a shifter of the diet.
But
and so we want to rescale it.
So if the Krispy Kreme also is a random effect, random factor for some other thing,
then you're in trouble. Then it's not a good instrument. Yeah, that would violate what's called the exclusion restriction. It only matters to mortality through the diet. That's it.
Okay, that makes sense.
Yeah.
And then you mentioned the term weak instrument.
Yeah.
But how do I know if my instrument is weak or strong?
If your F statistic is less than 10, your instrument is
question about what an F statistic.
Right, yeah, fair point. Basically, the strength of your instrument has to do with the regression of the treatment on the instrument. So when you regress low-fat diet on distance to Krispy Kreme, basically what you want to see is that the distance to Krispy Kreme really matters. And the particular rule of thumb, people are laughing because this is the particular rule of thumb people like is that the F statistic, like the T statistic squared, is bigger than 10. A larger relationship, a more significant relationship, bigger, that's better. And if it's weak, then there are some things you can do about it. But in practice, people just look around for a different instrument most of the time. All right.
Let's thank Emily again.
So again, I'm going to go to bed.